Hi, good evening. I will just wait for a few more minutes and then we can start. Um, hi, good evening. Can you tell me if my screen is visible?
Yes, sir.
Thanks, Anjali. So I'll just start now. Welcome to this final session on the course Advanced Power Electronics and Control. So today will be the final session wherein we will try to actually conclude whatever we have been seeing so far in the past few weeks, past 8 weeks, right? So I will try to include as many diverse problems as possible from different topics, right? So that you are well equipped for the exam. Okay. So just summarizing a little
Okay.
bit. Yeah. So just summarizing a little bit, you went through power semiconductor switching devices in the week one, that is first week. So wherein you read about ACRs or thyristors, then you went through GTOs, that is gate turn-off thyristors, and then you went into MOSFETs, BJTs, and then IGBTs and stuff. So you learned what was switch realization and wherein you tried to understand the operation of the switch using the quadrants, right? So you had the first, second, third, and fourth quadrants. So you tried to categorize switches based on whether they are one quadrant devices, two quadrant devices, or four quadrant devices. And even in that, you had distinctions such as voltage bidirectional and current unidirectional switches such as the ECRs, or you have the current bidirectional and voltage unidirectional switches such as MOSFETs, right? Or IGBTs for that matter. So you went through different types of devices and a little bit into the semiconductor technology, right? So then you went into AC DC conversion, which are known as the rectifiers, correct? Yeah. So you went into AC DC conversion. That is, you went into rectifiers, wherein you studied the uncontrolled rectifier using totally diodes. Then you went to the semi-controlled or half-controlled rectifier, right? Wherein you have a combination of both diodes as well as ACRs, and then you went into fully controlled rectifiers, correct? Wherein it is made up of totally rectifiers. And then you also learned that, okay, within these itself, you can have multiple topologies based on whether the AC system or the AC supply is single phase or three phase, right? Okay, and towards the conclusion of this topic, that is AC-DC conversion, AC-DC converters, you also went into a bit of the impact of the inductance, right, or the source inductance. So how does source inductance actually affect your conduction time and stuff, right? So you went into a bit of that and you studied its impact in single phase and three phase, right? Full bridge and semi-controlled rectifiers. Okay, so after completing rectifiers, you went into DC-DC converters or the switch mode power supplies, okay, wherein you went into a bit of chopper operation, you studied the basic topologies such as the buck boost and then the buck boost converters, okay. After that, within this itself, I guess we saw problems based on how to find out the switch current, RMS values, average values and stuff, right? So after which you went into inverters, that is DC AC converters, correct? So again, you went to half bridge, then full bridge, and then of course the three phase topologies. You studied what was 120-degree conduction mode and 180-degree conduction mode, correct? So these were some topologies and some control techniques you studied, wherein you went into a bit of different types of PWM techniques, right? So you studied what was unipolar, PWM, bipolar, sinusoidal PWM techniques, then uniform PWM technique, right? And then you went into a bit of space vector modulation and stuff. Okay. Third harmonic addition and space vector modulation and stuff. Okay, so this was about inverters. You studied topologies as well as some PWM techniques. Okay, so you, after studying AC-DC, DC-DC, and DC-AC conversion, you finally came to AC-AC converters, right? Wherein you went into a bit of AC voltage regulators, right? And then you went into cycloconverters, and then you studied some matrix converters, correct? So this is where I guess most of the converter topologies ended. After that, you also had a session which was the last week based on power quality issues, correct? So you went into a bit of passive and active filters, and in that you have categories such as the series filters and shunt filters. Basically, filters are just LNC elements tuned to a particular resonant frequency, right? So that they kind of shunt out or remove harmonic of that particular frequency. Okay, so you are now, your total current is now one harmonic order less. Therefore, your THD will obviously improve and stuff. Okay, your power factor is going to improve. The idea is that you always want to draw a sinusoidal current from AC. Okay, so this is with respect to AC, you always want a unity power factor one. And with respect to DC, you want a pure DC. That's the idea, right? So based on these two principles only, you have different kind of topologies. Maybe in your more advanced courses you will study more converters which enable almost unity power factor, or um, correct, or which enable converters wherein the filter requirement is lesser and stuff. But anyway, in the basic power electronics course you studied a lot of these, right? You studied a combination. Okay, so today we will try to solve problems from all of these topics, and that should kind of summarize whatever we have seen so far, correct? So since this is kind of a problem solving session, I will try to restrict my discussion mostly towards oriented towards solving more problems and not going into more theoretical aspects. Okay, and of course, at any point of time, if you have any doubts, you can stop me and ask very well. Okay, thanks. So. So before we start summarizing or before we start solving problems, I would like to note down some points which are kind of effective or essential, and they will definitely help you solve problems. Okay, so I'll just note them over here. Some important points. Okay, so mm, okay. Okay, so some things. you might have to remember is that an L is a current stiff element, right? Or it's a I stiff element. It never allows sudden change in current. And similarly, C is a voltage stiff element. It never allows sudden change in voltage. Okay. And what's the energy stored over here? The energy stored is half Li square. And this is basically half CV square. Okay. And one particular relation which denotes the relation between V and I in the time domain is V is equal to L di dt and I is equal to C dV dt. Okay. So this is just some basic stuff that I wanted to cover over here. Okay. And then you of course have um okay, so how do you relate L and C to your impedance, right? So dimensionally we tell that root over L by C, right, is equal to V by I. Okay, how do I tell it? If I kind of equate the energies, half Li square is equal to half Cv square, correct? So the half and half will get cancelled. So what you will end up is this. Root over L by C is equal to V by I. This is in ohms. Okay. So this is also what is called as a characteristic impedance. These are just some circuit concepts, okay? So which I thought it might be helpful for you guys. Okay. So if I can move ahead, right? So in your entire power electronic course, you would have come across different waveforms, right? For example, okay, so before I go into waveforms, let's say in any question that is concerning with AC, let's say they tell a 230-volt supply, right? Let's say the question says a 230-volt AC single phase supply and so on. Let's say it's feeding some load or something like that, or a rectifier or whatever. So if only the number alone is given, it is always the RMS value. If only the number is given, it is always the RMS value. If let's say it was given as 230 sine 2 pi ft or sine omega t, only then this 230 will be peak value Vm. Okay. If not, if only the number is given, it is always an RMS value. Okay. Fine. So we will go into some waveforms that you saw so far. Okay. So you know this, correct? So what is its RMS? Vrms is equal to Vm over root 2. This is something you know, correct? And let's say the waveform is something like this. Okay. So what is the average value over here? V average is 0, obviously. Okay. So Vrms for this is given as okay, so this is nothing but a single phase full bridge rectifier, right? Like your both waveforms are getting rectified, correct? Both in the positive half and the negative half. So Vrms will be given by Vm over root 2. So you guys, it will be better if you can note this down anywhere. This waveform thing is actually really good. I found this helpful whenever I was preparing for some exams or stuff. Okay, it's a quick reference, just like a thumb rule. Okay, so the Vrms for a rectified wave is Vm by root 2, and V average is obviously not 0. So what is its V average? It will be 2 Vm over pi. So this is something that you might have seen in your rectifiers module, but anyway, V average is 2 Vm over pi. Okay. Okay. And then you have this one over here. Let's say half wave rectified. So this is a full wave rectifier and this is a half wave rectifier. So what is its Vrms and Vm average? Vrms will be given by Vm over 2. Okay. And V average is going to be halved, right? So Vm by pi. It's not 2 Vm by pi. It's now going to be Vm by pi. Okay. And then finally, let's say you have a triangular wave. Okay, you can always find out its RMS in the exam. It's not a problem, but it will be better if you can, if you have these in your mind directly. Okay, it will help you reduce time. So the VRMS is going to be VM by root 3, and the V average will be VM by 2. Okay, so what are these waveforms? So this is your um, sine, and then this is your full this is your full wave rectifier, and then you have this as your half wave rectifier, and this is your sawtooth. Okay, you can always find out what is VRMS, V average by just solving it by knowing the basic definition of VRMS and V average, but it will be better if you can, if you already know this. Okay, fine. By the way, what's the definition of VRMS and V average? Um, Let me go over here. So V average is given as 1 by T integral 0 to T f of T dt. Okay, or this is the area of the curve over T period. And what is the V RMS, or the root mean square, right? So it's a root, and then it's a mean which is getting squared, f square of T dt. Okay, so 1 by T integral 0 to T f square of T dt. So this is actually root mean squared. So if I tell that I'm squaring it, right? If I tell I'm squaring it, it means that basically I am taking the modulus, correct? Because if I square minus 5 and if I square 5, I'm going to end up with 25, right? So basically, I'm getting a mod of whatever, irrespective of whatever is the sign of f of t, I'm getting a mod of the square, correct? So you need to remember that it's always going to be a positive number. Okay, so it is positive. Okay, and let's say if I have a function v is equal to a plus b sine omega t, correct? So what is the average value? The average value is going to be just a, correct? Because the average value of b sine omega t is 0. Okay. And what is the RMS? RMS is going to be root over a square plus, so the RMS of a is a. And what is the RMS of b sine omega t? RMS of b sine omega t is b by root 2. Therefore, the total RMS is going to be root over a square plus b by root 2 the whole square, or a square plus b square by 2. Correct? Okay. So v is equal to a plus b sine omega t. Average value is going to be just the DC component, because anyway the sine terms are going to cancel out for average. And what about the RMS? RMS, individually you take the RMS. Correct? So individually you just take the RMS and then square it up. So root over a square plus b by root 2 the whole square. Okay. Okay. So what do these RMS and average values indicate? So basically, hmm, basically RMS, or the root mean square, is used in problems if, let's say, they ask something like what is the heat generated or heat dissipated. Always note that you need to use the RMS component, I square R. I RMS square into R. Okay. It is always associated with heat RMS. Okay. Whereas what is the average? Average is basically, if I tell average voltage, it means that this much amount of charge has been transferred to the capacitor across the voltage, correct? So it is something like charge transferred. Okay. So generally, let's say they ask questions like what is the um, power loss across the resistor? Then you use I RMS square into R. But if they tell what is the power delivered, right? So be aware of the terminologies, okay? If they tell what is the power delivered, then it's always going to be a V naught I naught or average, V average into I average, okay? So it's always going to be a V average into I average. Hmm. Okay. So generally, and one more rule is generally, if you see the power factor of rectifiers and power factor of cycloconverters, they are very low. Why? Because they use SCRs or thyristors. Therefore, the input current is going to contain a lot of harmonics. Okay. Input AC current. Therefore, generally we tell that the power factor for rectifiers or cycloconverters, they are generally very low. Okay. Fine. Okay. So then, okay, with this knowledge, we will go into rectifiers or maybe a little bit about power semiconductor devices. Okay. Hmm. So if I just have to list out the devices, right? So you have the power diode, which is uncontrolled, and it is always unidirectional current conduction. Okay. And then you have SCRs or thyristors on the other hand, they are semi-controlled. Why semi-controlled? Because turn on is controllable, whereas turn off is uncontrollable. Okay. So they are semi-controlled. So SCR is basically uh, voltage bidirectional, right? And current unidirectional. Okay. Voltage bidirectional and current unidirectional. Correct. So and then you have the MOSFET, which is fully controlled. Okay. That means both turn on and turn off are controllable. Okay. That is turn on is also controllable. Turn off is also controllable. Okay. So in the case of a MOSFET, it is current bidirectional and voltage unidirectional. Okay. So for MOSFET, it is current bidirectional and voltage unidirectional. Hmm. Okay. And then you have what is called as BJTs or IGBTs, correct? And then you have track. Okay, so let me go to track. So track is also fully controlled because you have two SCRs in anti-parallel, correct? So you can control both the turn on and turn off. Okay, and it is voltage bidirectional, and current bidirectional. So it's a 4-quadrant operation, right? So this is where you went into quadrants of operation, right? So you studied about different quadrants of operation. You identified where each device is going to lie. For example, the power diode will be over here, correct? So this is your power diode, which is always in the second quadrant. Okay. And then you have your ACR, right? So for ACR, um, okay, so let me just note it down. So diode is in violet, and then you have your SCR. For SCR, it is voltage bidirectional. Okay. So for SCR, it is voltage bidirectional. Therefore, it is 2-quadrant operation, 1 and 2. So this is only in the second quadrant. This is in 1 and 2. Okay. What about MOSFETs? Um, for MOSFET, you will see that the operation is current bidirectional. Okay. So it is in first and the fourth quadrant. Okay, so like this, you can always do switch realization. So you can have combinations of these and you can try to identify where the switch is operating, correct? So I think we solve problems on that as well. Okay, and finally you have the triac, which can kind of operate in all quadrants. Okay, that is both voltage bidirectional and current bidirectional. So triac can operate in all quadrants. Okay, so you did study about the switch operations and stuff. Hmm. Okay, so since we are studying about triac, you can always tell since triac is fully controlled and it is voltage bidirectional and current bidirectional, it can be used for. So triac is okay. If I go to the new page, okay. So triac, since it is uh, voltage bidirectional, current bidirectional, 4-quadrant operation, it can be used for purposes such as AC phase control or used in multi-quadrant choppers and stuff, wherein you need to move across different quadrants, first quadrant, second quadrant, third and fourth or stuff. Okay, so you can always use triac. Okay. Okay, and then typically we also saw earlier that SCR is used for high power and very low frequency operation. Okay, whereas MOSFET on the other hand is used for lower power and very high frequency operation. Okay, very high frequency operation. Okay. And then whereas you have the IGBT somewhere in the middle, wherein the power is also a little high. So this is high power and medium frequency operation. So what are the frequencies you are talking about? SCR cannot operate more than maybe 100 hertz or 300 hertz or something like that. So less than hundreds of hertz. Whereas a MOSFET can operate till around more than 1 megahertz. Okay. IGBTs are operated until up to 20 megahertz. Okay. So this is the frequency range we are talking about. Okay. Fine. So apart from this, you have the GTOs, right? Wherein you have, which is both a latch on plus latch off device, right? So you have GTO, which is a latch on plus latch off device and improvement over ACRs and stuff. Okay. Fine. Okay. So in the four quadrant operation, so what are the names of all of these quadrants? So this is called forward blocking. Forward blocking. Okay. And then it's called, mm, let me name the, okay. So this is called forward conduction. And then this is called reverse blocking. And finally, we have reverse conduction. Okay. Forward blocking, forward conduction, reverse blocking, and then reverse conduction. Okay. Okay. Yeah. So one more thing we saw was because track has a four quadrant operation, it can be used for AC phase control, multi quadrant choppers, or it can also be used for speed control of multi quadrant choppers, or you have what are known as universal motors. Correct? I guess we saw this problem in the previous lecture as well. Track can be used for speed control of universal motors. Okay, fine. So then we came across power diodes, right? So how are power diodes formed? Or any power device formed? You have what is known as a N minus drift region, right? So this drift region actually gives its high voltage blocking capability. The width of the drift, for example, in a power diode, right? You have P plus, N minus, and then N plus. Okay. So this N minus is actually your drift region. So the width of the drift region, okay, the width of the drift region WD is proportional to your blocking voltage. More the width of the drift region, more will be the blocking voltage. Okay, so that's how people manufacture 650 volt, 900 volts, or 1200, 1700 volt devices. However, one drawback is that width of the drift region also influences your on-state loss. That is, whatever is the forward voltage drop or the RDS on of the MOSFET, all of these will increase with the width of the drift region. So you cannot use a 1200 volt MOSFET for a 100 volt application. The reason is that the losses will be really high because the VF and the RDS on will also be higher in that case. Okay, so the width of the drift region is also increasing with, I mean, as the width of the drift region increases, your on-state losses will also increase. Okay, fine. So particularly in the power diode, you saw what was known as the reverse recovery, right? So you had something like this. Okay, or typically, if I have to redraw, typically people tell that this is really high compared to this. Okay, so okay, so the entire area over here, correct? So let me call this as ID, diode current with respect to time, right? So basically this is IRR, reverse recovery current. And the area over here is basically QRR, reverse recovery charge. Okay, and then you have what is known as TRR over here. Okay, and then you have TA and then TB. Okay, so people generally tell even though TRR is equal to TA plus TB, TB is very, very less than TA. Therefore, your TRR is almost equal to TA. Okay. Therefore, you can assume that this itself is a triangle, right? Because basically you have something like um, okay. So this is basically a triangle, and that's how we derive all the equations, right? So this is your IRR, and this is your QRR, and you have TRR. Okay. So with knowledge of either of these, you can always derive what is your IRR, TRR, or QRR and stuff. Okay, fine. So what is QRR? QRR is basically half into base into height. So half into IRR into TRR. Correct? This is your QRR. Okay. So this is the relation between, and let's say the slope is di by dt. Okay. So in that case, what will happen? Di by dt, if you assume that the slope is linear, then it is going to be basically IRR into TRR. Okay. So this is the relationship QRR you have, and then you also have what is the di by dt. Okay. Fine. And one more thing is that we were telling the width of the drift region increases the on-state loss. Also, the width of the drift region increases the reverse recovery loss or the TRR. So the reverse recovery time will be higher, right? If your reverse recovery time will also be higher if your width of the drift region is more. Okay, so you just cannot use very high voltage rated diodes for all applications because your reverse recovery will also increase significantly. Okay, fine. Okay, so after diodes, you went into SCRs or you went into SCRs, you studied the VA characteristics, and then we studied what was the latching current, what is the holding current and stuff, correct? So latching current is something that's related to the turn on process, correct? So we need to give that much gate signal until the current through the SCR increases beyond IL or the latching current. So until your SCR current increases latching current, you need to keep on giving the gate signal. Okay, and what is the holding current? Holding current is related to the turn off process. So if I might write it for SCR, IL or the latching current is related to turn on process. And IH or the holding current is related to the turn off process. So before turning off the SCR, you need to ensure that the SCR current reduces below the holding current. Only then you have to apply a negative voltage to turn off the SCR. Okay. And then during turn off, you also studied what is known as the circuit turn off time and the device turn off time. Okay. So what is the device turn off time? It is the period or the interval time for which you have to apply negative voltage to the SCR. Correct. And what is the circuit turn off time? Circuit turn off time is the period for which the negative voltage is being provided by the external circuit. So you have to ensure that TC or the circuit turn of time is more than your device turn of time. Okay. And the relation is basically TC is equal to TD times some safety factor. Okay. So the safety factor is always greater than 1. Correct? Okay. So this is what we went to over here, and then okay. Okay. So we will just perhaps solve one problem over here. Okay. Problem number 1, that is, let's say you have something like this. Okay. So in what all quadrants the device is going to operate? That is the question. Find out the quadrants of operation. Okay. So find out the quadrants of operation. Okay. So just try to identify what all are possible. Forward conduction or forward blocking, forward conduction, reverse blocking, and then reverse conduction, right? So these are the four um, possible operating states of any device. So how will these operate? So you try to understand until you give gate pulse to this ACR over here. Until you give gate pulse to this ACR, the device will not conduct. Okay. Therefore, forward blocking is possible. Correct? And then of course, if you give gate pulse to this ACR, then the device will conduct, right, in the forward direction. Therefore, forward conduction is also possible. Okay, this is a polarity and this is what we call as forward conduction. Okay, so forward conduction is also possible. Is reverse blocking possible? If you apply a reverse voltage or a negative voltage, if you apply negative voltage, this diode is going to conduct. Okay, therefore, only reverse conduction is possible. Reverse blocking is not possible. Okay, because this diode cannot block voltage, correct? Therefore, it can operate in 3 quadrants. What are those 3 quadrants? It can operate in forward blocking mode. It can operate in forward conduction mode. And it can, of course, operate in reverse conduction mode. Okay. So these are the 4 quadrants of operation. Okay. Fine. So let's move ahead with the, sorry. Okay. Let's move ahead with the next question. Um, yeah. Find the pulse width required to turn on the SCR if its latching current is 50 milliamperes and holding current is 40 milliamperes. Find the pulse width required to turn on the SCR if the latching current is 50 milliamperes and holding current is 40 milliamperes. Okay. Okay. And the circuit is as follows. So the circuit is, we have the ACR over here. And then this is 100 volt, 20 ohms. This is 0.5 henries and it is 5 kilo ohms. Okay. So first point is the question is about the turn on process, right? And we just saw some time back that during turn on process, what comes into play is a latching current. So they will just give holding current but however holding current holds no significance in this problem. Okay. So just use latching current for your problem. So what is the current over here at this node? It has two parts, right? Therefore, what I can write is ISCR is equal to I1 plus I2, correct? So ISCR is what? IL, right? It is the latching current during turn on. So what is I1? So I1 is the current through the RL branch. What is the current through RL? It is basically V by R into 1 minus e power minus t by tau. Okay. Plus, what is I2? I2 is basically V by R2. Okay. So this is the answer. You got it. Therefore, your IL, which is 50 milliamperes or 0.05, is equal to V by R1. That is 100 divided by R1 is 20 ohms into 1 minus e power minus t. This is what you want, the pulse width, right? Or the TP. You want to find out what is TP divided by tau. So what is tau? Tau is basically L by R plus V by R2, that is 100 by 5K. Okay. Got it. So I will just pause over here for you guys to note it down in your copy or something. Okay. Okay. So then what happens is, therefore your 50 milliamperes is equal to V by R is 100 by 20, which is 5 into 1 minus e power minus t by. So what is tau? Tau is L by R, right? So L is 0.5 by 20. That is 1 by 40, correct? So 1 by 40 goes to the numerator, it becomes minus 40t. Minus 40t, correct? Plus 100 by 5k. So what is 100 by 5k? That is 1 by 50, which is going to be 0.02. So from this, you can find out what is TP. Okay. So TP, if you calculate, will turn out to be around 150 microsecond. So you need to give a pulse width of 150 microsecond to ensure that the ACR turns on with a latching current of 50 milliamperes. Okay. So this is the pulse width, required pulse width. Okay. So if this is fine, we will move on to rectifiers. Okay. So we have seen a lot about the semiconductor devices. We will move ahead with rectifiers now. Okay. So what are some essential considerations for rectifiers? One thing you saw was that you have different categories such as uncontrolled, then semi-controlled, and fully controlled. Okay, in uncontrolled, you have only diodes, and in semi-controlled, you have both diodes and ACRs, and in fully controlled, you have only ACRs. Correct? So if you have uncontrolled, you are converting a fixed AC to fixed DC, right? So you don't have any control over its DC value. Whatever is the AC, it will convert it to a corresponding DC, correct? That is uncontrolled. Whereas in semi-controlled and fully controlled, you have control over the AC, right? So you can have fixed AC to variable DC. If you vary the pulse width, correct, or if you vary the alpha or the firing angle, you are going to get different average values. Okay, so you are going to get from fixed DC, you are going to get a variable DC, right, which is dependent on alpha, correct? DC value dependent on alpha. Okay, so because of the SCR, you get this controllability. Okay, so these are the categories you saw, and you of course categorize them as one pulse rectifier, two pulse rectifier, three pulse rectifier, and six pulse rectifiers, and you have 12 pulse, 18 pulse, and so on, multi-pulse rectifiers. Okay, so of course, so these two for single phase, and these for three phase, and then so on. Okay, so this is how you categorize the rectifiers, different kinds of rectifiers. Okay, and then you went into a bit of numeral or the uh, nomenclature, correct? So you saw different definitions over, right? So you saw what was the form factor, that is V RMS by V average. Okay, and you saw what was ripple factor. So ripple factor is basically root over form factor square minus 1. Okay. This is, so in examples they may give in exam. So if the form factor is this much, find out the ripple factor or vice versa. So simply just use this formula. Ripple factor is root over form factor square minus 1. Okay. Or the ripple factor is basically what? Ripple factor is basically your RMS of the AC component in output divided by DC component. Or you can tell it is VRMS divided by VRMS of the output divided by V average. Okay, in the output side. That is why to avoid confusion with the form factor, I'm writing it as this. That is the RMS of the AC component in the output divided by the DC component. Okay. Then what? So how do you find out the ripple voltage? The ripple voltage is basically just the AC component, right? So it is root over V RMS square minus V average square. Okay. So form factor, ripple factor, and ripple voltage is basically root over V RMS square minus V average square. Okay. If you have a pure DC, right? If you have a pure DC, then form factor is 1. That is V RMS is equal to V average. Okay. And then ripple factor is 0. There is no ripple at all. Okay. Therefore, the ripple voltage is also 0, obviously. Ripple is equal to 0. Okay. For a pure DC. Okay. So then you also saw what was distortion factor. Correct. So distortion factor or G is the RMS of fundamental component. RMS of fundamental component, I am writing it as RMS 1 divided by the RMS of the total component, total RMS. So RMS of fundamental divided by the RMS of total. Okay, RMS of fundamental divided by RMS of total. 1 is fundamental, T is total. Okay, and what is total harmonic distortion? THD. How is it related to your G or the distortion factor? THD is basically root over 1 by G square minus 1. Okay, so if you have one, you can find out the other. Okay, so if they give you what is distortion factor, you should be able to get THD and vice versa. THD is root over 1 by G square minus 1. That is distortion factor square, 1 by distortion factor square minus 1. Okay, so for a perfect AC wave or a pure AC, right? For a pure AC, it will be composed only of the fundamental, right? No harmonics. Therefore, RMS fundamental is equal to RMS total. Therefore, the distortion factor is 1 and the THD is going to be 0. Correct? Distortion factor will be 1 and the THD will be 0. Okay, fine. Okay. So then you saw one more definition, which was called as the transformer utilization factor. TUF, right? So it is the DC output power or the PDC divided by the VA rating of the transformer. Okay, effective VA rating. That is V naught I naught divided by VS RMS into IS RMS. V source RMS into I source RMS. Okay. V source RMS into I source RMS. Okay. So what is V source RMS? V source RMS is going to be VM by root 2. Correct? And if you have a pure resistive load, only if you have pure resistive load, I source RMS is going to be V RMS over R. If you have a pure R load, or else this does not hold good. Okay. So transformer utilization factor is PDC divided by the VA rating. Okay. Fine. Then, okay. Hmm. Then we saw a lot of problems on calculating the V naught, right? For semi-controlled or full bridge rectifier or half bridge rectifier, controlled and uncontrolled, right? We saw a lot of problems on finding out V naught. So finding out V naught, what is the VRMS? Correct. What is the power delivered, right? That is V naught I naught. And what is the power dissipated or the power lost or the P lost? That is I RMS square into R or V RMS square over R. Okay. So we saw a lot of problems on these. Okay. Problems. We saw a lot of problems on these. Correct. Okay. Okay. So one thing we derived in detail was that for single phase, right? For a single phase case, the G or the distortion factor is 0.9. We derived it. I'm not going through the derivation again. We wrote the harmonic, the Fourier series for the source current, correct? So the Fourier series was something like the source current IS is equal to sigma n equal to odd to infinity 4 I naught by n pi sin n omega t plus phi n, correct? Where your phi n is equal to minus n alpha, where alpha is the firing angle and n is the harmonic order. So once you have the Fourier series, you can find out what is G, right? Because G is basically fundamental RMS divided by total RMS. Okay. So that turned out to be 0.9 for a single phase. So since G is 0.9, THD is root over 1 by G square minus 1. Root over 1 by 0.9 square minus 1, which turned out to be around 48%. Okay. Therefore, THD is only 48% or useful component, right? Useful component which is delivered to the load. Useful component delivered to the load is only 52%, right? Because 48% is gone as harmonics, correct? THD is 48%. Okay. So this is for a single phase case, right? So this is something we saw. And then we of course saw problems on what is the thyristor current or the SCR current and what is the diode current in case there is a freewheeling diode, right? So we saw how to compute the RMS and the average. The trick is for each converter, if you want to find out what is thyristor current or the diode current, draw the converter, okay? Draw the converter and then you try to recognize when the thyristor is on, when the thyristor is off, when the diode is on, when the diode is off in the entire cycle. Okay, from that you can calculate what is the thyristor current or the diode current very easily. Okay, fine. We saw converters with RLE load as well. Problems with RLE load. Okay, wherein you have a battery. In that we saw problems with both conversion as well as inversion, right? So when does inversion occur? If alpha more than 90 degree, correct? In a single phase case. Okay. So you saw that power can be delivered back to the source in this case, right? P back to source. Power is delivered back to source in this case. Okay. Yeah. So mm, okay. Then after completing single phase, you came to the three phase case, right? So we studied three phase, and in that as well, we saw, okay, in the single phase, most dominant harmonic, right? Most dominant harmonic is the third order or n is equal to 3. Okay, in single phase case, the most dominant harmonic is n is equal to 3. However, in three phase case, you will see that most dominant harmonic is going to be n is equal to 5, fifth order. Therefore, you will see that you can intuitively understand that the TSD is going to be much better, right? TSD is going to be much lower compared to single phase case. So over here, we derived that your G, right, or the harmonic distortion factor, I'm sorry, distortion factor is basically derived as 0.95. Over single phase, you saw that G is 0.9, right? So for three phase case, the G is 0.95. Therefore, the THD turns out to be around, if I remember right, it is around 30. Yeah, it is around 32.86% or 32%. Therefore, the useful component is 68%. Okay, therefore, you get better utilization of power or more power is delivered to the load, you can tell. Correct? Okay. So this is, and in three phase, you saw different converters, uncontrolled and controlled. And finally, you studied, we solved some problems on three phase case as well. So single phase, three phase, controlled and uncontrolled. And finally, we studied the effect of source inductance. You saw some problems on these as well. Okay. How it affects the conduction angle. We have an overlap period over here due to the effect of source inductance. Okay. So what is the overlap period? So you have something called as the overlap period, right? Wherein both the outgoing is CR and incoming is CR conduct. Okay. That is the ACR which is going to turn off and the ACR which is going to turn on. Both of them will conduct for a very small period of time. That period is called as the overlap period and they come about purely due to your source inductance. Okay. So this is where we ended up our rectifier discussion. Okay. Single phase, three phase, controlled, semi-controlled, uncontrolled, and then finally effect of source inductance. And of course, we studied different terminologies such as ripple factor, distortion factor, harmonic factor. What is the ripple voltage, total harmonic distortion for single phase and three phase, and we derived each of these. Correct? Okay. So this is mostly about your rectifiers. So I'll just give you guys a breather of 1 or 2 minutes. Okay. So we will just resume in just around 2 minutes. Okay. Okay, so we'll just resume. So far we have covered power semiconductor devices and um, you know, rectifiers, right? So we will move ahead with inverters right now because I feel inverters is much more important to rather than DC-DC converters. I believe you will be much more proficient with that. We will also see that eventually, but first I would like to cover inverters. Okay, fine. So inverters, you of course know, they convert from fixed DC to a variable AC, correct? This is the function of inverters. So you have two kinds of inverters in that you have the grid connected inverters or the standalone inverters, right? So for grid connected inverters, you of course know that you don't require any force commutation for ACRs because the line voltage itself is winning sinusoidally, right? However, for standalone inverters, you are switching the devices actively. Okay, so you need force commutation circuits for standalone inverters. Okay, or people generally tend to use IGBTs or MOSFETs in inverters rather than ACRs. Okay, so in ACRs or in inverters itself, you have three categories. That is voltage source inverters, you have the current source inverters, and you have what is called as the series inverter. You of course studied different other inverter topologies, that is the Z source inverters and stuff, but I'm not going into that because from the aspect of problem solving, what you will be seeing is basically voltage source inverters. Okay, so why do we call it voltage source inverter? The reason is that the output voltage is held constant, correct? Or based on the switching, the output voltage is always fixed, right? Whereas the output current depends on the load. Depends on load. So the output current is load dependent. Dependent on the output load, the current will vary. Okay, for current source inverters, it's going to be vice versa, right? Okay. So in this, we saw problems from basically single phase half bridge VSI, right? And then we have single phase full bridge VSI, okay? And three phase VSI, 120-degree conduction, and three-phase VSI, 180-degree conduction. We basically solve problems from these four categories mostly, correct? So if you are aware of these four, then I think you should be able to ace inverters questions. Okay. Okay. For current source inverters, you of course know that the output current is held constant and the output voltage is load dependent. Okay. Fine. Okay. So, so you studied single phase half bridge VSI, correct? So in this, you saw problems on how to find out the output voltage RMS or the V naught RMS, correct? So what is the power delivered? Power delivered, correct? And what is the peak current via any switch? What is the peak current via any switch? And what is the average current via any switch? So basically, you should be aware of how to solve how to obtain V naught RMS because V naught average is obviously zero. Then what is the power delivered, peak current through any switch, and the average current. Okay, so this was one category. Then you had to solve the Fourier expression, right? So you know that the Fourier expression is going to be something like n is equal to odd. For half bridge, it will be 2 Vs by n phi. For full bridge, it will be 4 Vs by n pi sine n omega t. So this is V naught. And if it's a purely resistive load, I naught will be V naught by R, correct, with the same harmonic content. Okay. So if someone asks you to find out the total power, it will be V naught I naught. If someone asks you the fundamental power or the useful power, it will be V naught 1 into I naught 1 RMS values, of course. Okay, V naught 1 or the fundamental component into IRMS 1, correct? Into cos phi, but anyway, over here you have a resistive load, therefore cos phi is 1, correct? So you saw problems based on these. That is the V naught RMS, power delivered, current through any switch, peak current or the average current. Then you went into harmonic order, right? And then you found out how to find out the useful power, correct? Or the fundamental power. Okay. So this was for a single phase half bridge VSI. Then you went into what is called a single phase full bridge VSI. Okay. And you learned that the output current can be something like this if it's an L load. Okay. Let's say that the output voltage is something like this, correct? So output voltage is something like this. Then in that case, the output current may be something like this. If it is L load, the output current can be something like a square wave if it is R load, correct? And if it's an RL load, you can get if it's an RL load. Okay. And if you have RLC, you can obtain some kind of resonance and get sinusoid even. Okay, if you have RLC loads. So you understand that based on the kind of load, the current shape is going to vary. And we saw problems on this as well. Correct? I mean, some theoretical problems on, okay, if you have a square wave VSI, then for what kind of a load you will get triangular or you will see this RL charging kind and stuff. Okay. Okay. So again, for all of these, we saw how to calculate the uh, harmonic, right? That is n is equal to odd to infinity. Over here, it will be 4 Vs by n pi sine n omega t. Okay. And I naught will be 4 Vs by n pi divided by z impedance, correct? Into sine n omega t plus phi n. Why phi? Because if you are having an RL load, the current is going to lag the voltage, correct? So this phi n gives a lagging angle. Okay, so Zn is actually R plus J into n omega L. Okay, where n is the harmonic order and phi is actually n times. Um, so phi is basically n times tan inverse omega L by R. I'm sorry. So phi is basically tan inverse n omega L by R. Correct? N omega L by R. This is your phi. Okay. So in this also we saw problems calculate the third order harmonic, first fundamental, fifth order and stuff, or calculate the most dominant harmonic for single phase or three phase. It will vary based on that. Okay. Calculate the harmonic power corresponding to the third harmonic and stuff. Right. And we also saw problems on what is the peak switch current, average switch current and stuff. Okay. Of course. What is the source current and stuff. So these are some kind of problems that we saw. Okay. Or for how much time the diode will conduct, how much time the switch will conduct. Okay. So these are some things that we saw. Okay. Fine. Okay. So after we completed single phase, we migrated towards three phase, correct? So first in three phase, we saw, sorry. So in three-phase, we saw what is known as the 120-degree mode of conduction. Okay. So in this, we found out what is the RMS value of the line voltage, RMS value of the phase voltage. Okay. And then what is the um, power delivered to the load, correct? And then RMS value of thyristor current, RMS value of thyristor current, and then finally the Fourier series expressions. Okay. And the same thing we repeated for 180-degree case as well. Okay. RMS value of line, phase, power delivered. What is the RMS value of the thyristor current, average current, and then the Fourier series. Okay. Okay, fine. So over here with problems, we were able to see that typically in delta configuration, right? You get more power compared to star. With a problem, we explained that in delta configuration, we get 3 times more power. P delta, we get 3 times more power as we get in star configuration. Also, the power seems to be higher in case of 180-degree mode. Correct? Obviously, because more number of diodes are in conduction, so more power is getting transferred. Correct? Or more ACRs are in conduction, right? At the same time, therefore, more power is getting transferred. So P in 180 degree is more than 120 degree, and P in delta is 3 times P times star. Therefore, the highest power yielding thing is you connect in delta configuration and operate in 180-degree mode. Okay. So typically, this is why you will see that generally capacitor banks, for example, capacitor banks, right? They are typically connected in delta configuration. So always you will see that capacitor banks that you will see in your power systems, they are connected in delta. The reason is that you can get more reactive power. Okay, so this is just a side information, but capacitor banks are typically connected in delta because you get more power, 3 times more power connect compared to if you connect it in star. Okay, power delivered is obviously higher. So this one we explained with an example problem, but you just need to remember that the highest configuration is P delta in 180-degree mode. Okay, fine. So over here, can anyone of you unmute and tell me if you want to have some kind of a formula reference over here for um, single phase and three phase, 120 and 180-degree mode? Do I need to give the formula or something like that?
Yes, sir. Yes,
Okay,
sir.
fine. So then I guess it will be easier for you, right? As a quick reference. Okay, fine. I will just write over here. So in that case, we will be compromising a little bit on your DC-DC converters, okay? Because I guess DC-DC converters you all may be well aware of because it's one of the more easier topics compared to inverters and rectifiers. Okay, fine. No worries. We can just go through that a little faster. Okay. So let me write single phase half bridge. Okay. So what single phase half bridge. Okay. So one thing is what is your Fourier? V naught is going to be sigma n is equal to odd to infinity. 4 into it's actually 4 Vs by n pi, right? Generally, but in a half bridge, you have Vs by 2, correct? 4 Vs by 2 by n pi or 2 Vs by n pi sine n omega t. Okay. So I will write this as 2 Vs by n pi sine n omega t. Okay. Fine. So what is the peak current via switch or I switch peak, if I might call it? It will be V naught max over R in case of a pure R load. Okay. So what is V naught max? It's going to be your same, right? Half bridge, it's going to be the same as your input voltage or Vs. So Vs over R, Vs by 2 over R, correct? Because it's a half bridge. So, or Vs by 2R, correct? So I will rewrite this as Vs by 2R. Okay, this is the peak current. And what is the average current? Each switch is in conduction for 1/2 of the time period, right? Therefore, Vs by 2R into 1 by 2, 1/2 of the time period. So the average is basically divided by 2. So Vs by 4R. Okay. So I will just draw the waveforms. So this is your V naught and this is your I naught. Okay. Is this fine? I'm just drawing it in a very small fashion for you guys. But I just wanted to tell the formula over here. But okay. So you can understand that S1 will conduct over here and S2 will conduct over here. Correct? Okay. So S1 is on for T by 2 out of T. That is why I have multiplied by 1 by 2 for average current. Okay. Okay, fine. And then we will go to the single phase. So can I go to the next slide? Can you please unmute and tell? Is this fine? Have you noted it down?
Yes, sir.
Okay, fine. So then we will go ahead with single phase full bridge. Okay. So for single phase full bridge, the V naught or the Fourier series expression will be n equal to odd to infinity 4 Vs by n pi sine n omega t. Okay. And I naught will be sigma n equal to odd to infinity if you have RL load. Okay. So it's going to be 4 Vs by n pi over Zn, right? Into sine n omega t plus phi n, where Zn is the equivalent impedance at that particular harmonic. So R plus n times j omega L. Okay. And phi is the lagging angle, which is tan inverse n omega L by R. Okay. N is the harmonic order. Fine. Okay. So this was about your single phase full bridge. Correct? And so can I move to the next slide, please? Hello? Can I move
Yes,
to the
sir.
next
We've
slide?
noted it.
Sorry?
Yeah, we've noted it down.
Yeah, fine. So then we have three-phase VSI and let's say 180-degree case, right? So in that case, what you will see is, I guess you have derived all of these in your regular classes. I'm just noting the formula. Okay. So VRMS of the line VRMS is going to be Vs into root over 2 by 3. Why? It is basically Vs into root over T on by T, right? Okay. So you can understand that each of the ACRs are going to conduct for 120 degree out of 180 degrees, correct? So root over 120 by 180 is the formula. So root over 120 by 180 is root over 2 by 3. That's why I have written VR is VRMS line is Vs into root over 2 by 3. So what is the phase? Phase RMS is going to be V line RMS divided by root 3. Correct? Therefore, Vs into root over 2 by 3. Simple, right? So if you know one, you know the other. Correct? So, okay. So what is the power delivered to the load? Because it is three phase, it is going to be 3 into I phase square RMS into R. Okay, or you can also write 3 V phase RMS into I phase RMS. Okay, cos phi is 1 obviously. Fine. And what is the RMS value of thyristor current? Yeah. Correct. So what is the RMS value of thyristor current? It is going to be the RMS value of phase current into root over T on by T. Okay. Each thyristor conducts for 180 degree. That is the idea, right? That is the idea behind 180 degree conduction. So I phase RMS into root over 1 by 2 or I phase RMS by root 2. Okay. So this is the thyristor current. Got it? Can I move to 120 degree case?
Yes, sir.
Is fine. Okay, so for 120 degrees, you will see that your V, yeah, V line RMS will be Vs by root 2. Vs is your DC voltage, mind you. Okay, if your V line RMS is Vs by root 2, V phase RMS is going to be Vs by root 6, correct? Vs by root 2 divided by root 3. Okay, so it is going to be Vs by root 6. Okay, and then you will see that the thyristor RMS current will be I phase RMS into root over T on by T. So 120 divided by 360. So I phase RMS into I phase RMS by root 3. This is your thyristor RMS current. Okay, over in 180 degree, you saw it was 180 by root 2. In 120 degree, it is I phase RMS by root 3. Okay, fine. And then what will be your thyristor peak current? In both cases, it will be I phase peak, correct? That will be the peak current in both cases. Okay. So these are just some quick reference formulae for you guys. Is this fine?
Yes, sir.
Yes, sir.
Okay. So after you saw the topologies, you went into a bit of PWM, right? So you saw different kinds of PWM, that is uniform PWM, then unipolar, bipolar PWM, sinusoidal PWM, correct? And then you ended up with space vector PWM, right? Okay, so in all the cases, you note that VRMS is equal to Vs into root over T on by T. This is the idea. Okay. For example, if you have the simple PWM or the uniform PWM, VRMS will be Vs into root over 2D by pi. Okay. What is 2D by pi? Let's say you have a square wave, right? Or it's a sinusoidal wave. Then you modulate it something like this. Okay. This particular region is called the pulse width or 2D. Okay. And this is your pi. Therefore, the on period is 2D and the total period is pi, right? In one half cycle. So Vs into root over 2d by pi. That is the formula for simple PWM. Okay. So you also saw that to eliminate a particular harmonic, to eliminate a particular harmonic, pulse width should be what? Pulse width should be basically 2D can be is equal to pulse width, or 2D is a total whole, okay? 2 pi by n, 4 pi by n, and so on. So this should be your pulse width. So for eliminating fifth order harmonic, your pulse width should be 2 pi by 5 or 72 degrees. Okay, 4 pi by 5 is 144 degrees and so on. Okay, like that for third order harmonic, you will have a particular pulse width and stuff. So you can vary your pulse width so that this particular harmonic gets eliminated. So this is something we saw, right? So this is for simple PWM. So if you properly select the pulse width, you can eliminate that particular harmonic without even needing a filter. Okay, because generally if you see power converters, the size of the power converter will be taken up by the filter alone. So to eliminate a particular harmonic, if you use a particular pulse width, right, then that particular harmonic gets eliminated without even requiring a filter. So that's the advantage of simple PWM. Okay. Okay, and then what we see? Um, yeah, so then you came to sinusoidal PWM. Okay, so you came to sine PWM, wherein you saw that the pulse width is going to vary in a sinusoidal fashion. Correct? So the over here you saw that if M is your modulation index, right? So what is modulation index? Modulation index is basically VR by VC. Okay, where or I should not use R. Let me use V reference by V carrier. Peak value of your reference divided by peak value of your carrier wave. Okay, generally the carrier wave may be a sawtooth, and reference in this case is a sinusoid, right? So this is your modulation index. If M is your modulation index, okay, this is the peak value. Vref and V carrier are the peak values. If M is a modulation index, then maximum value of um, output voltage is going to be M times Vs, right? Or M times VDC, or however you may call it. This is the maximum value, and your RMS value or of output voltage will be M times Vs over root 2. Okay, simple, right? Because it's sinusoidal PWM, you just divide by root 2. M times Vs over root 2. Okay. So more the number of pulses over here, more the number of pulses or more the N, right? The smoother will be the waveform. It is more approximated towards sine wave. Okay, so that is the idea. More the N, the better it is. Okay, fine. Um, Okay, so this was about sinusoidal PWM. We predominantly will see problems in PWM from only sinusoidal PWM or the simple PWM. What is the pulse width and VRMS? And similarly for sinusoidal PWM also, what is the modulation index and what is the maximum value of output voltage and what is the RMS value of the output voltage? Okay. Okay, fine. So um, can I go ahead to the next slide over here? Okay. So finally, we will conclude inverters with a small discussion on current source inverters. Okay. So current source inverters or CSI. So for current source, you always have a voltage source and a large inductor in series. Okay. Okay. So in current source, the waveform is going to be something like I naught will be a constant square wave, whereas the V naught is going to change with the load. Okay. If it is a pure capacitive load, you understand that I is equal to C dV dt. V is equal to L di dt. Correct? So if it is a pure capacitive load, you can understand that your V is going to, if you have a constant current over here, right? If you have a constant current, then for a pure capacitive load, then your voltage will increase, right? dV dt. Your I is positive. If your I is positive, dV dt is positive, right? Therefore, voltage rises. That is why your voltage will increase when the I is positive. When the I goes negative, voltage will decrease. Okay, this is completely opposite to voltage source inverters. In voltage source inverters, you saw that if your V is a square wave, then your inductor current will be inductor current will be triangular, right? V is equal to L di dt. Over here, it is a complete opposite analogy. Your I is a square wave, therefore your capacitor voltage will be a triangle. Okay, it's a complete opposite analogy. Okay, opposite to VSIs. Correct? And of course, if it's a R load, the voltage is going to be like this. Got it? So, and what will be the Fourier of this current? I naught, correct? I naught will be simply 4 Is by n pi sin n omega t. Okay, let's say this is your current Is. Okay, so you have a constant current source Is over here. Then in that case, I naught will be 4 Is by n pi sin n omega t. Okay. And what will be V naught? V naught will be I naught multiplied by whatever is the impedance. Impedance can be, of course, R plus J omega L or stuff. Okay. But anyway, it is, you just replete Vs by Is. Okay. So you got it? Any doubt in current source inverters or inverters in general itself? So we have concluded inverters. So we saw single phase half bridge, single phase full bridge, three phase 120-degree and three phase 180-degree. All the formulae we saw for VSI, and finally we ended up with CSI. And of course we saw PWM techniques of uniform PWM as well as your simple PWM as well as your sinusoidal PWM. We just saw the formulae, and finally we ended up with CSIs, current source inverters. Okay. So is this fine with you guys? Any doubts so far?
No, sir.
Okay. So we will just start off with DC-DC converters, and um, we will conclude over here. Okay. Basically, in DC-DC converters, you will be seeing problems from buck boost or buck boost converters, and maybe a bit on critical conduction mode. You won't get any problems with discontinuous conduction as such, but yeah, of course, you may expect problems with critical conduction mode. Okay. Mm. So, or sorry. So finally you come to choppers or DC-DC converters. Okay. So why did people go for DC-DC converters? Basically because to convert from one DC to another DC, to convert from one level of AC to another level of AC, you have transformers, right? But you obviously don't have transformers in the DC, correct? A transformer cannot convert one level of DC to another level of DC. That is why people had to go for choppers and power electronics came into play. Okay. And basically, that is why choppers are also known as DC transformers. DC transformers. Okay. Because they convert one level of voltage to another level of voltage. You take the case of buck boost or buck boost, it converts one level of voltage to another level of voltage. Okay. So they are used for DC drives applications and stuff. Okay. So what do choppers do? They convert fixed DC to variable DC. You have control over the DC component. Okay. So in this, you studied about the buck boost and buck boost converters. So, should I go through the explanation or can I directly just go through the formulae? Um, okay, I think we are desperately short of time. So I will just go through the formulae, okay? So that it comes in handy for you guys. So for buck converter, you of course know the basic that V naught is D times Vs, where D is your duty, V is your input, and Is is equal to D times I naught. Complementary, right? So this is V naught average. What is V naught RMS? It will be root over D times Vs. Okay. And what is the average inductor current? Inductor is in the output side, therefore average inductor current is I naught. Average inductor current is I naught. And what is the current through the active switch or the current through the MOSFET, right? The average current through the MOSFET will be D times um, D times I naught, and the average current through the thyristor is going to be, or the through the diode is going to be 1 minus D times I naught. Correct? Okay. D times I naught, or it is Is. Okay. So what will be the RMS current through the switch or the MOSFET? Root over D times I naught. And RMS current through the diode is going to be root over 1 minus D times I naught. Is this fine so far? So basically you will be seeing problems from this. Okay. Okay. So then we went into calculation of what is the critical conduction mode, or how do we relate what is the necessity of the LNC, right? Or what is the requirement of LNC? So you saw that your delta IL. By delta IL, I mean the peak to peak ripple, okay? Imax minus Imin. Peak to peak ripple. Imax minus Imin. Some people use 2 delta IL and stuff. So I am defining delta IL as the peak to peak ripple. Peak to peak. Delta IL is equal to D into 1 minus D into Vs divided by your switching frequency into L. So from this, for a given specification of delta IL, you can find out what is L. Okay. Also at higher frequencies, your L value is going to be smaller. Correct? Similarly, your peak to peak voltage ripple delta Vc will be D into 1 minus D into Vs divided by 8f square LC. Okay. So you can find out what is your C value from this. Correct? Okay. And what is your critical inductance? Critical inductance is computed as 1 minus D by 2F into output. Okay. And critical capacitance is computed as 1 minus D by 16 F square LC. So guys, I will urge you not to mug up these formulae. Do not mug up. Okay. I'm just writing, but do not mug up. Just understand if it is critical conduction, you know that IL is equal to delta IL by 2. Use this relation over here. You get the answer. Correct? IL equal to delta IL by 2. Simple, right? Or similarly, V naught is equal to delta Vc by 2. Okay, use the relation, you get the answer. Okay, even you need not mug up these. This is just V is equal to L di dt. I is equal to C dV dt. Okay, you just need to understand the working. Okay, this is how we solve the problems. We never use these formulae. Please do not mug up these formulae. Okay, or maybe it will be better if I don't just write these formulae. I'll just write the switch conduction and stuff. Okay, fine. So for a boost, oh. So next we come to the boost converter. You know that V naught is equal to Vs by 1 minus D. Is is equal to I naught by 1 minus D. Correct? And average current through the switch will be D times Is. Average current through the inductor. Inductor is now is in the input side, right? Therefore, average current through the inductor is the source current. Average current through the diode will be 1 minus D times Is, correct? Or I naught. Okay. And RMS current through the switch will be root over D times Is. RMS current through the diode will be root over 1 minus D times I naught. I'm sorry, Is. Okay. To find out what is L and C, just use V is equal to L di dt. I is equal to C dV dt. To find out the critical value, use IL is equal to delta IL by 2. Vc is equal to delta Vc by 2. What is IL over here? IL is basically Is, correct? In a boost converter. Is is equal to delta IL by 2. Just solve. You will get what is LC and CC. Okay, but more importantly, you need to know these. Again, if you know the operation of the converter, all of this is easy. You can just tell, right? MOSFET will conduct during the D interval. Therefore, the average current is D times Is. Diode will conduct during the 1 minus D interval, right? Therefore, it is 1 minus D times and stuff. Okay. Do not mug up these. So, yeah. And finally, we will come to the buck boost converter. Correct. So V naught is equal to Vs into minus D by 1 minus D, or minus Vs into D by 1 minus D. Okay, because the polarity is kind of opposite, reversed, right? Is is equal to I naught into D by 1 minus D. Okay. So what is the average current through the inductor? The average current through the inductor will be IS by D or I naught by 1 minus D. Okay. And I switch average or IM will be D times IL. Okay. IM RMS will be root over D times IL. Similarly, I diode average will be 1 minus D times IL. A diode RMS will be root over 1 minus D times IL. Okay. Fine. So I'm not going to go through your AC voltage regulators. So AC voltage regulators, I guess you just saw some time back, right? So, yeah. So do you guys have any doubts so far in whatever we have seen? You can please let me know. Or you want me to tell you something else or any other topic that you want me to cover?
No, sir.
Okay, fine. Or maybe I'll just add a small um, hack for AC voltage converters. Okay. For cyclo converters, mostly the problem is going to be cyclo converters. Mostly the problem is going to be find out the RMS output voltage. RMS output voltage will be Vs into root over T on by T. Okay. Where T on is the number of on cycles. Number of cycles for on state. Number of on state cycles. Okay. And T is the total number of cycles. Basic definition, total number of cycles. So this is for cyclo converters. Okay. And for AC voltage regulators, we saw what was the VRMS, right? With single phase R load and RL load, R load, and then RL load. So I'm not going to the formula. The formulas are there in the slides itself. You need not mark them up. Okay. However, you note that for RL case, at a particular value of phi, the converter becomes uncontrollable because the output voltage will become continuous. Okay. So you will see that if your triggering angle or the firing angle alpha is less than phi, correct? Then the converter becomes uncontrollable. Okay. Well, what is phi? Your phi is basically tan inverse omega L over R. Okay. At a particular value of alpha at a particular value of phi, if your alpha or the firing angle is less than that phi itself, then you see that the converter becomes uncontrollable. You just need to know the angle. And if your alpha is more than phi, you will see that it is controllable. That is controllable means you will have a discontinuous wave. Whereas if it is uncontrollable, you will have a continuous wave. I think we saw this in the lectures, I mean in the problem solving session itself. We solved 1 or 2 problems based on this. So this is just a hack. Okay, fine. Okay, so since you guys don't have any more doubts, I would like to conclude over here. This marks the conclusion of the problem solving sessions on the advanced power electronic course. Today it was more of seeing where all we can get problems and how we can solve them kind of, right? So I think I have covered in detail the power electronic switches and then rectifiers we covered in detail, then inverters as well was covered in detail, and then we went through DC-DC converters and finally the AC-AC converters. Okay, so I would like to wish you the best of luck for your um, upcoming exams. Okay. Yeah, all the best. So I will stop the recording over here. If you have any doubts, you can go ahead and ask, or else I will stop the recording. Okay.